I understand that we have a long afternoon, but okay, let me try to get into the issue right away. All right, so I think we are 4. So if you remember last time we were doing this morning, so I'm going to be constructions of instability, right? Okay. Yeah, remember the equations. That's always important to remember. It's like that. Okay, let me say a few things just to be clear. So V on the boundary, okay, just have space equals 0. And what was V? So remember that this is the equations, and V, our V is the U nu minus U Prandtl. Okay, and for simplicities, I'm going to check the Prandtl, which is just a function of U that doesn't depend on time. Okay, doesn't depend on time, and so this is the exact Navier-Stokes. This one is the stationary boundary layer, and L is the linearized operator, right? Linear operator around UBR, right? UBR, and of course I could write out explicitly for you just in case, just in case. Okay, so it's UPR dx of a vector V minus V2 dy UPR and 0 minus the pressure, where's the Laplacians, plus a new Laplacian of V. Okay, so this is the exact problem that we wanted to do, and the question is, remember that the question is, okay, we wanted to bound the difference and say to control the difference. In fact, that's what we do. All right. Then I make the scaling, right? I make the scaling, and I just, okay, maybe I should not cheat. Make the scaling. So the equations. So my equation is the same, right? It's the same. Maybe I should. My equation is the same. I should just make a scaling right here for you already. I make a scaling for you already so that I don't have to do it again, okay? Because I'm going to do everything in subnorm. So if you don't mind, I just replace this by y, because I already make a scaling. So everything is the same except this one is square root. Okay? That's all I'm changing, in fact. Okay? That's very good. That's some. All right, and of course that give you a bound which is not useful at all. Of course, this is essentially useless. Okay, which is yeah, in this case it's exponential of C0t, because I already scaling. All right. So this one is not useful, but this morning I said, now the constructions, we start, let's say step 1, we start with, so to start with an unstable mode, okay. Of course, I wanted to understand the difference, but remember that this operator is the observations of the linearized operator of Euler around a shear flow, and that could be stable or unstable. And so now let me just start with the one that is already unstable of Euler. Okay, so I start with the one of Euler, which is, let's say, C Euler. Alpha 0 x minus C0t Okay, phi Euler y. All right, where alpha 0 is positive, the sign does plus or minus, it doesn't matter. So alpha 0 is positive, and imaginary part of C0 is also positive. Okay, and so I could get some any bounds, and this phi solving phi solve Rayleigh. Okay, Rayleigh equations. So I start with that, and I could even assume that here I could take the one, I could take the most unstable mode. Okay, meaning that the because the linearized operator of Euler, there's only unstable, countably many unstable mode, so I can take the maximum one, and I can start with that. Okay, so let me just start with unstable one of Euler, and step 2. From here, I construct an unstable mode of Navier-Stokes. Okay, and this mode looking like this. So it's VC of Navier-Stokes. It still have the same form. Still have the same form. Alpha x minus CT. Okay. This is the mode of OS. All right. This is the mode of OS, where the point is that this mode of OS is going to be the mode of Rayleigh or Euler plus a boundary layer. Okay, plus a boundary layer of the form like that. Maybe it's not super clear to you what's going on, but let me recall the OS equations, which is Asymptotic equations. OS is Asymptotic. Equations. Okay, it's exactly Rayleigh. So the second order ODE equal epsilons. Okay, second order ODE. So this one is second order. This one is Rayleigh. Yes, right. Epsilons is square root of viscosities over I alpha. So it's a complex number, but we're going to do perturbations around this alpha 0 is positive and fixed, and C0 is positive and fixed. Oh, sorry, C0 is complex, but imaginary part is positive and fixed. And so this is just the regular singular perturbations. I was prepared to do the examples for that, but okay, the interest of time, let me just instructions. But the point to say is that this one as y equals 0 is equal 0, and y prime y equals 0 is also equal 0. Okay, and phi as y equal infinity is equal 0. And so you see that the Euler mode, so phi e of Euler, phi e of Euler is equal 0. Okay, on the boundary, but there's no reasons for phi e prime of Euler to be 0. Okay, no reason for that on the boundary, and so just the hint that the L is to correct the non-zero boundary conditions, right? So explicitly, phi BL is the one that I can construct so that VBL prime, yeah, so VBL is y equals 0 is equal to 0, but VBL prime derivative at y equals 0 is supposed to cancel whatever the non-zero of V Euler. Okay? Okay. And this is just the ODE constructions. A small point to make is that because the imaginary part of C is non-zero, and so this this C, so C is not, so C is not in the range of U, and this is important in fact, because C is not in the range of U. So this is again is still singular perturbations, but it's regular singular perturbations in a sense. Okay, because there's no issue here. Okay, and Emmanuel in the afternoon, he may talk more about the case when C is actually in the range of U. Okay, this is where all the issues come in. I mean, at least they're already at the level of linear. Okay, so for me, let me just do that case that everything is fine. Now, so what I'm saying that so now VC is a growing mode. Okay, a growing mode. VC is a growing mode of Navier-Stokes. Okay, yes. And the point is that this one has two parts. One is, maybe let me just write explicitly here. This one has two parts. I want to discuss a bit more about this here. So this one has two parts. The first part is the Euler, and the second part is the boundary layer. Okay. And not to confuse with the Prandtl boundary layers, we call this one boundary sublayer. Boundary sublayer. All right. And what is the size? Square root epsilons is the square root of nu over I alpha. And alpha and C are near alpha 0 and C 0. So, and alpha 0 is near 1 or a positive constant. So this is nu 1/4. Okay? So maybe the picture to keep in mind with all these scalings, because there's too many scalings, that I already made one scaling like that, which is square root nu. Okay, so right now I'm solving these equations. I'm solving the Navier-Stokes equations. These are the true Navier-Stokes equations with the viscosity square root nu, right? Meaning that I'm solving the equations sent in. And the growing mode that we have is the Euler part, maybe Euler, or you can call it Rayleigh part, and the boundary layer part. So the sublayer. So the sublayer is the layer of the size. The scaling is of the size nu 1/2, and then you scale one more, you get nu 1/4. Okay, so nu 3/4. All right. So the picture is that. Okay, you look at the problems essentially very near the boundary, and you do around a shear flow that is already unstable to Euler, meaning that the shear flow that could have inflection point, let's say a shear flow of this form. So this is a picture of shear flow. And the linearized problem already gives you a growing mode. Okay, the linearized problem give you a growing mode. There's some estimates for growing mode that I'm going to use. Maybe let me just say the growing mode that I'm going to use. Okay, so VC LP norm is bigger than exponential of real part of lambda 0 t. So this is so it's growth. It's growth like that. By the way, it's a growing and it's linear, so I can put any constants in front of it as I like, right? So can you just put a delta in front, because I don't have to rewrite it. Just put a delta in front. Okay. So the growing mode is have size delta, where delta is I'm going to choose later. Okay. And what more important is that the gradient of VC, the subnorm, is bounded by, and this one is upper bound and lower bound in fact. Yeah. Okay. The gradient is, you have delta, exponential of real part lambda 0 t. Okay. Here, plus nu minus 1/4. Okay. All right. Because this is VC, it's already one derivative, and I take the gradient, so I take another derivative. Okay. So like that. The gradient and the L2 norm. The L2 norm is growth like that, 1 plus this one is the L2 norm, so it's nu minus 1/8. Okay. The fact that 1/8 it's only because this one is localized, this one is so phi BL in practice, actually in the constructions we really have of the exponential of minus y square root nu. Okay, essentially exponential localized, because just know the solve. And so if you take L2 norm, yeah, you get a bit. Yeah. Okay, that's what I'm going to use. Actually, I use more, but let me do the first try. And then you see that from that equations, then you see that, all right, you said V is and hence to let's say to capture the growth, right, the instabilities of VC. So you have the growing mode, and the standard thing to capture some growing mode. What do? You let V tilde, or you let you write V, your nonlinear solutions, to be VC plus V tilde. Okay, as a thing to do. And so you dt, the equation for V tilde. So this is one. It's just first one is just a linear, and it's equal. But remember that what is the nonlinear? Nonlinear is like this. So you get a few terms. Okay, you got a few terms like V. You got a few terms like V dot gradient VC. Okay, VC dot gradient V. All right, V dot gradient V. Okay, V tilde, sorry. V tilde. Okay. And then by now I already done 1, 2, or 3 times of energy estimate. So now it's completely trivial. I think that it's safe to say that V tilde, maybe I even do it a bit even quicker. Energy estimate plus Grenier. Hence, okay, say if you don't like, say V tilde. All right. L2 in time is less than, by the way, V2 da, you can take V2 da at t equals 0, okay? Because if you can prove that V2 da is always remain smaller than VC, then you really capture the instability, okay? So it's equals 0 to t, okay? Say, and this is important, say if you don't like exponential of I'm going to write explicit, in fact, exponential of, I already cancelled the 2, so exponential of gradient of u Prandtl in the new scaling, okay, plus gradient of Vc, okay, plus 1, because I'm generous, plus 1, yes, plus 1, and then I have t minus s. All right, so basically what I'm doing is that really the the semi-group, there's only linear part, right? So this thing come in here. Heating this guy, heating Vc dot gradient Vc L2 no, okay, S ds. This is what you will get, okay, after a ground wall. All right, and then you realize that, okay, very good. So this one, you do a bit more calculations. You said, all right, this one is 0 t. This one exponential of 1 plus, so this gradient of Prandtl is 1, okay, it's 1 or C0, okay, because I'm scaling, I'm already scaled, so plus gradient Vc is, I can put it there, okay, so it's very explicitly delta exponential of real part of lambda, okay, 0 t, and then 1 plus nu minus 1/4. All right, so this one is exactly in the exponential t minus s, okay, and this calculation is actually important. In fact, it's almost almost as important as anything. So this one I get delta square, because Vc is about the size delta, Vc is the size delta in L2. So in L2 I lose just a little bit. So I have 2 real part of lambda 0 t, and then I have nu minus 1/8 ds. Okay, and is it here that you hope to get, because actually this is the standard nonlinear analysis that you do, exponential of the semi-group bounded by nonlinear, you wanted to get exactly the same thing. Oh, sorry, this is S, right? This is S, okay? You wanted to get exactly the same thing, meaning that you wanted to get C0 delta square, or maybe delta square, I even write this way because it look nicer, 0 t square and nu minus 1/8. Okay? Of course, all right. Okay. Now, if you don't pay attention, then I'm in trouble, because star never accept. Oh, not never hold. Sorry, stars holds precisely, or provided what is constant, whatever is constant in front that I did, provided 1 plus c plus delta exponential of real part lambda 0 t 1 plus minus 1/4, whatever in the exponent less than 2 real part of lambda 0. Does it make sense? So you think of that as calculations as exponential of the semi-group, right? The semi-group hitting the remainder, okay? Hitting the remainder, okay? And you wanted to get back exactly the same of this guy. The I mean, you can only do that. So let's say the sine of this is, let's say, C1. You can only get that if C1 is less than 2 real part of lambda 0. Okay, so this analysis that I did essentially is the analysis, let's say, you can find in, I mean, this is standard linear to nonlinear instabilities. For instance, in the nice notes by Bados, Gauss, and Strauss. Okay, and of course this. So this is what you need, and this may not be always true. Then may not be always true. First, let's see. Suppose this is okay. Okay, which means that you require a lot of things, right? Which means that you require at least 0t. You need to be less than nu 1/4. So that's the first thing you need. Okay, or is it holds provided, or maybe to even more precise, provided, or as long as, right? As long as, even if you want it to be more precise, as long as this is true. So you need this to be less than nu 1/4, and suppose this was the case, then of course what did I do? V is equal Vc minus V tutor, and so V, my L2 norm is bigger than Vc, L2 norm minus V tutor, L2 norm, and this is delta exponential of lambda 0t. Okay, and minus this guy I said, if that was true, then it's square something. So yes, 0 delta exponential of real part minus 1/4. Sorry, 1/8. Okay. All right, but this one is already a constraint. So for instance, this one is bigger than, because I wanted this guy, so I wanted delta real part of lambda 0t 1 minus C0 delta real 0 t nu minus 1/8, and this guy is like less than or required to less than 1/4. So in total it's more. So we see that this one is bigger than, or which means that this one is always bigger than delta t. Okay, which means that I'm t star okay. I have to be more precise. Okay, let me be a bit more precise. What I said that now, if this was already the case, then you get this, and because as long as this is true, so which means that you can go up, which means up to the time t star, so that delta exponential of real part lambda 0 t star equal, let's say, 1/10 nu 1/4. Okay, you can go up to that point. Then the VL2 is bounded below by delta real 0 real part of lambda 0 t star at t star, sorry, at t star. Okay, which is equal 1/10 of nu 1. Okay, which all right, which means that what I just need, at least to tell you that at least I can prove the instabilities, the lower bound of the nu 1/4. Okay, and in fact, I mean, as long as this is true, and so this exactly explain the issues that I said this morning. Is that if you have this picture, okay, if you have this picture, And if you get these pictures, and the size of sublayer, so V, because V is like VC, okay? So the Reynolds number in this box is the Reynolds number in this box is this U, or is the sign of VC over nu 1/4. Okay, so this energy estimate I do, it stops at nu 1/4. Okay, and all right, that was, of course, this is the obstructions. Right? So the sublayer is a series of obstructions to go beyond that. Okay, so the question is the goal, or maybe rather the questions: can we go beyond nu 1/4? Okay, which means that you need a longer time in a way, because you want to somehow go beyond nu 1/4, right? Nu 1/4. You want it to go beyond nu 1/4. Okay, meaning this one can this one go beyond nu 1/4? Okay, what to fix the history of what's going on? I mentioned Barros, Go, and Strauss, where they need the spectral gap, meaning that, of course, they don't deal with the boundary layers, but I haven't said anything about this guy. Then, of course, the analysis I did here, in fact, is done in the nice paper by Emmanuel Grenier, where he fixed this gap, in fact. So, the idea is, let me just roughly the idea very quickly. In fact, I'm not going to do more because I wanted to do. The idea is that, all right, you start. The idea is that now V, instead of just taking VC, okay, instead of just taking one growing mode, which is delta of, which is instead of just taking the summations in J from 1 to big N of delta J Vj. Okay, so the idea is to not just start at the remainder. So the idea is not just to take Vj, which is V1, not just to start with Vc only. So the first one is start with Vc, which is of order delta lambda 0 t. But to solve for V2 or Vj iteratively, okay, and Vj solving iteratively in the sense that solving the linear Vj equal, because you have only one nonlinear term, v dot gradient of v, so you have vk dot gradient of vl k plus l equal j. All right, and the point is that if you keep doing that, then up to when n is large, if you keep doing that n times, I recommend you to look at these iterations, because it's very nice. You keep doing that, then you replace the quadratic by a nonlinear term of power n. Okay, so this is like a normal form analysis, in fact. So this one, so you see this one is like delta to the n exponential of n real part of lambda 0 s, and so the gap issues, the C1, so n large enough for the gap issues. It's no longer an issue if you take n large enough. Okay, so iterate so n large enough. Okay, so the first issue was resolved in this paper by Emmanuel. talk, at least I'm trying to do now, is to fix this issue. So what? So is there a clever energy estimate to do that? It's turned out that so the leading shear flow is, you already have it here, and the sublayer is also of some kind of form of shear flow. Sublayer is also of some kind of form of shear flow of this ansatz. And in a linear paper that we did, we actually proved that for any shear flow, you always have instabilities. It's always unstable, in fact. Meaning that even this shear flow, you, at least linearly, you would have another sublayer which is smaller, 7, 8. Okay? So the idea is to try to remove, or at least to avoid. You see what I mean? So I'm doing the analysis on this scale, and I have the sublayer up here, but the sublayer by itself is also unstable, and we have to find a way to avoid the growth of this, because the linearized operator is not stable. Okay. Is it still okay? All right. And so there was the crazy idea is that, in fact, the crazy idea is almost here, is that you take the sum and you treat the remainder. What I'm trying to say is that this remainder, this one is very unstable, right? It's unstable because, okay, no matter how you subtract, do the normal form up to the order n with a very small error, you still have to solve the Navier-Stokes equations, okay? Because V theta is solving Navier-Stokes equations, right? V theta, the point of V theta, I mean, it's already here. Maybe I don't have to write down this V theta still solving. Maybe just in word, this V theta solve, because the remainder solve Navier-Stokes around U approximate, okay? U approximate solutions, where U approximate is exactly these crazy summations that we have, okay? All right. But approximate solutions have crazy gradient, because the gradient, as I computed somewhere, is delta rho 0 t, but then 1 plus nu minus 1/4. Okay. In fact, if I haven't said it, delta is we could take anything, so we're going to take nu to the m very big, okay? So be very, very small. All right, so you still have to solve Navier-Stokes around something that is unstable, and to control that is lost. And the idea that we did, so this is maybe 5 or 6. We call it a complete constructions, instability, constructions. Okay. For ansatz, we're going to take something that is crazy that you should not try at home, because we're going to take the infinite sum. Okay. So the first thing is that we take the sum is infinite. Okay. But if you look at here, I solve this iteratively. At the step j, I solve it depend on everyone j minus 1 before, and every time I do that, I have loss of derivative. And if I take, I'm going to lose infinitely many derivatives. Okay? And the idea here, what allow us to be able to take these terms without worrying about lots of derivatives and be able to make them converge is exactly the idea of generator. So, so let me introducing this norm, and I'm going to do some computation with that norm. Okay? Is it clear for everyone what's going on? So, right, this is the whole point. Yeah. This is the whole point. Yeah. Yes. To be able to construct a functional space to do analysis. Yeah. So, maybe right. So, right. Okay. Anyway, so I'm going to do introducing. Generator, in fact, generator. Okay, so we generator functions. Okay, I'm going to just say something small about it, and so the norm 0 u is going to be the functions in alpha, the summation in alpha, and then summations in beta. Okay. Summation in alpha, summation in beta, exponential of z1 alpha, and then sub in y of derivative in beta. Okay, in y of u or y alpha. So hat is stand for Fourier of Z2 beta factorial. Okay, so this is nothing but the analytic norm of u. The analytic norm of u. Okay, and we just like to do with the Fourier in x and derivative in y. Okay, this is nothing but analytic norm for u. And then the generator. Delta u, omega, which is supposed to be norm for vorticities. The same thing, g1 alpha sub in y of vorticity is crazy. Actually, this is wrong. This is wrong. This is more. C beta. I will explain. C beta, dy beta, okay, C beta of vorticity hat alpha y times the weight, which is 1 plus too many delta. Maybe let me just do too many delta, sorry. Let me do new minus 1/4 exponential of minus y new 1/4 minus 1. Z2 beta over beta factorial. Okay, so this is of course the analytics norm for vorticities. Okay, at least just to explain Py is this function y plus 1 over y. You expect that vorticities, the vorticity, the Fourier transform in alpha. So for x, we treat it as the mode by mode like that. But in y, if this is bounded, then in y you see that the behavior in y is supposed to be 1 plus nu minus 1/4, because we have to work with space that allows sublayer, right? Okay, this is the space allowed the sublayers. So, because this is behavior that we can avoid. All right, and then derivative. Then you wanted to have y dy remain bound. Okay, y dy remain the same as without derivative. Okay, so this is what you could say. This is the normal. So this you could call it. So there's a name. This is what we call a boundary layer. Analytic norm. How about that? Okay. Yes, please answer.
What is Z1 and Z2?
Yeah, great questions. Great questions. So this is the norm. It's a norm where Z1, Z2 are variable. Okay. That's a great question. That's important. Okay. So where you can think of Z1, G2, and G2 are the analyticities, radius. Okay, in X and Y respectively.
And U alpha is a Fourier transform.
Exactly. U alpha had is a Fourier transform in X, and W alpha is Fourier transform in Y. W is also a Fourier transform in X. And so this space, we need to design a space that to capture precisely the behavior of sublayer. All right, and in years, why do we do? First of all, we completely remove the remainder. Because remember that remainder, I mean, this is crazy, right? No matter how well approximated you are, you still have a remainder, and remainder solve the same equations, which is the Navier-Stokes equations. But the Navier-Stokes equation is very unstable at the boundary. So how to avoid that? We developed this framework, and it turned out that we never really have to solve Navier-Stokes. We really solve the resolvent equation, in fact, meaning just the ODEs. So at every step, we really just solving ODEs. Okay, so this way completely remove the instabilities of Navier-Stokes. That's one point. The second point, this norm it turned out to be super nice, because maybe I don't have time to prove, but you could trust me that the generator of U times W delta. So this delta is a bit crazy. Delta is supposed to be saying that it's the weight. The zero is saying that without weight. Okay. Delta is supposed to say weight. Okay. This weight is, or maybe bounded by the generator of U. I'm sorry. Exactly. So that's only right. Exactly. So sorry, because I'm using the delta for different things. Maybe let me just say delta 0. Is that, oh, sorry. No. I don't know. In paper we do delta. So delta. Yeah. So just a name. Okay. Just there's no delta here, but just a delta here. Maybe how about this? Generator of vorticity of W. Okay. Just to make a difference with this. That's all.
I understand, but the proposition.
Right.
Is the generator the product of which one between?
I'm sorry.
Okay.
Okay. Crazy. dx of generator wait, no. Generator of dx. So the norm of derivative is exactly derivative of the norm. I think you've never seen anything like it. Okay. Derivative of the norm is equal to normal derivative. Derivative of, let me be a bit careful. Derivative of this weight dy. So this is, so I mean, in short, this is the analytic norm. This is the almost the usual analytic norm with respect to dx and with respect to y dy. Okay, it's almost like analytic norm of dx and y dy, except that for vorticities we have to have a weight. That's all. Okay, and this is equal dg2 of generator w. Okay, so norm of derivative is equal to derivative of the norm. I think you've never seen anything like it for sure. And generator of u dx is bounded by generator. So this is u dx is still for vorticity is still like that. 0 u dg1 generator of w, and then generator of v dy. Okay, now u is supposed to be u1 and v is supposed to be u2. Okay, it's bounded by generator of u dg2 d1 of generator of u times dg2 generator of w, provided for dx u1 plus dy u2 equals 0. Okay, and you need the boundary conditions u2 y equals 0 equals 0. Okay, you see what I'm trying to do. To solve, I'm trying to solve because eventually we're trying to solve this, right? We're trying to solve the Navier-Stokes equations. Okay, we wanted to solve Navier-Stokes equations, and we're going to solve it in a way we're going to solve it solving an ODE, in fact. Okay, not quite because of this semi-group, but the point is that we find a norm so that, at least in our mind, you wanted to find a norm so that even this one is very unstable, but eventually the equation for the norm is looking like generator less than, or maybe even some more crazy norm less than dg, and g, we take z equal g2 in fact. Does that make sense? So we wanted to introduce a norm that you treat this BDs as an ODE in fact. Okay, because the point that this one, okay, have a loss of derivative, and because of loss of derivative, you have because of loss of derivative, you get the instabilities, you get a sublayer, and we need to work with a space where it allows this sublayer to live. And it turned out that we work very hard, of course, and this is the right space to
allow time dependence on Z1 and Z2 on the way, you know.
That's a great point. So after you get this, then now you can choose, you can place with the analyticity radius and close the analysis, in fact. And of course, this paper, maybe let me just say now, with remaining 1 minute, let me just say, or maybe this is probably enough here. It's probably enough here, just to say in case of you interested in. So the reference for this is, of course, I already said this is a joint work with Emmanuel, and it's on Institut, which is the approach that I mentioned here, the generator approach, because with the framework of analytics, then we don't see the sublayer, we don't see the smaller layer. That's important. That important number one. We don't see this smaller layer. That's important number one. The important number two. We never have to deal with remainder. And I could mention also that this approach we're able to work. We're able to understand with Grenier missing an R. Yeah. And we're able to understand these problems in other contexts also. So just of course, this is not the topic of talk here. With Roniansky on Landau damping. Because with the analytics, again, it's very flexible to treat the problems with one loss of derivative. And once you have one loss of derivative, and if you work in the space, in the right space, you treat the remainder or the nonlinear as a perturbations. The thing that I really the thing that I never mentioned, the thing that I never mentioned, what maybe I did, is that the choice of the weight, and the choice of space, eventually we come up that it's not out of sky. We come up that really relying on the kernel of your BD, in fact, the kernel of the linearized operator. So we work in the norm that it passed through nicely with the linearized operator, in a sense. Because eventually we solve BDs, but we really just working in the kernel of the linearized operator. But I think that's probably enough test of this problem for you. I mean, of this nonlinear problem for you, subject. Okay, I'm done. Thank you.